All right, so for this first one, we have that a medical center is testing patients for a certain disease, and that this disease occurs in 5% of the population. Then they follow up by saying that they test every patient who comes to the center on a particular day. And of course, for part A, to state the sampling method being used. Now, sampling method makes reference to like who do they survey? Okay, who do they test? And so who do they test? They test every patient. All right, so every is a word that's going to help us here. And also on a particular day. So those are two big hints for what sampling method is being used. There's usually around 5 sampling methods, especially at the IP Math AISL level. These are probably the ones you're going to be going through. Those. Okay, we have simple random, convenience, systematic, quota, and stratified. And so simple random in its name, it's kind of like you have a set amount of patients, you pick 10 of them, and you survey those 10. See? So in this case, it's not simple random because we are testing every patient. See, if you're testing every single patient, then it's not simple random. All right. Convenience in this case is correct. It's the easiest path, but you conclude that it's convenience mainly because it's not the other ones. Okay. And so I'll come back to that. All right. But for now, trust me. So it's not simple random because it's testing every single patient. It's not systematic because systematic would be something like, ooh, every 2 patients we test them, or every 3, or every 4, right? But not every single one of them. Quota would be something like you want your sampling method to end up with 30% young patients, 70% old patients. See? So in this case, there's nothing like that. Again, we are testing every single patient that walks through the door. And stratified forces you to split your sample or your population or whatever into groups. Okay, so this usually comes in the form of like, I don't know, like you make a sample with the ones that come in the morning and you make a sample with the ones that come in the afternoon. Okay, that could be a sort of stratified thing. Notice that it's different from quota. All right, the way that they make the groups is different. It's a different sort of criteria, and so it's not stratified. So it has to be convenience. So again, you cannot conclude in this scenario that it's convenience by going backwards. You go discarding the ones that are not, and you end up with just convenience. I know that's kind of weird, but it's also because convenience is kind of weird. I mean, the definition of the convenience sampling is like you're literally taking the easiest path. Okay. Um, so you usually reach that conclusion by discarding the other ones. All right. So, anyways, the sampling method being used is the convenience sampling, is what we would answer here. Convenience sampling. Again, you reach this because you are discarding everything else, but it also kind of makes sense. I mean, it's the lazy way. You just test every patient and you just forget about it. It's pretty convenient. Just saying. All right, we keep going. Then they tell us that it is intended that if a patient has the disease, they test positive. If a patient does not have the disease, they test negative. Makes sense. However, the tests are not perfect, and only 99% of people who have the disease test positive. All right, I'm going to take a moment right there. This, that is in purple, okay? So the tests are not perfect. Only 99% of people who have the disease, sorry, 99% of people who have the disease test positive. So have the disease, test positive. That's where this 99% is, okay? Have the disease, bada bim, test positive, bada boom. All right, that's how we got that 99%. So where does this 2% go? They tell us also 2% of people who do not have the disease test positive. I'm going to use another color here so that we know what's going on. I will be using, let's say, red, okay? So 2% of people who do not have the disease test positive. So do not have the disease, so it's going to be this way, test positive. Test positive this way. So that 2% is hidden on C. So this right here is going to be 2%. All right, that doesn't really look like a 2. Let me redraw it. I did not 2%. All right, so that's where this 2% just went. I am just inputting the information that the problem is giving me. You always want to double check that the numbers they give you are actually in your diagram. So the T diagram shows some of this information. See, so we had to fill in the rest of it. And actually for part B, we need to fill out all of it. So for C, we already know that it's 2%, and I should be able to figure out the rest on my own. How do I do that? Well, the cool thing about uh, tree diagrams, or the convenient thing, is that the probabilities add up nicely. What do I mean by this? The probability of any scenario has to be 100%. Okay? Like whether it happens or doesn't happen, you add it up together and it goes to 100%. For example, if you have a disease, there's a 99% chance that you test positive. See? So what's the chance that you test negative? Well, of course, it has to be 1%. Why? Because you're doing 99 plus x has to equal 100%. How do you know that it's 100%? Because this here has to equal 100. This here, also in orange, has to equal 100. And you guessed it, this here in orange also has to equal 100. A very common mistake is that people say this has to equal 100. That is the mistake, okay? It's a very common one, that's why I pointed out. Every like set of roots, if you want to call it, okay? What, like this would be one root, this is another root, since it is a tree diagram, ¿cierto? Has to equal 100%, all right? So each of those pairs has to equal 100%. Each of my orange circles has to equal 100%. So now that I said that, it's all going to come out very easily. See, for example, for this guy here, I'm going to say, well, 5% plus 8% has to equal 100%. Well, A has to be 95. Boom. If C is 2%, D has to be 98%. And B already made it, did it earlier, see? So again, this part is not particularly hard, but you do have to understand well how the tree diagram works. And the biggest hint I can give you is this thing that I drew in orange. See? What is important about it? Every orange thing equals 100%, and you work from there. Awesome. So we keep going. Part C. Use the tree diagram to find the probability that patients selected at random will do each of these thingies. Okay? So, in probabilities, there's buzzwords that can help a lot. See? These exercises in general, you want to look for buzzwords, and in the realm of probabilities, and is a massive buzzword. Okay? And I'm going to put it in text here. In the world of probabilities, we have that and is going to be a sort of multiply, and we have that or is going to be a sort of add. Okay? Later on, we have given, and it's just kind of like weird shit. But I'll go over that later. For now, let's focus on and or. So right now we have and, see? So that means we're multiplying. So we'll not have the disease. We said was no disease is A is 95%. So I'm looking at this path that I'm going to draw in, let's say, dark blue here. So we're going this path, ¿cierto? Not have the disease is A. A we said it was 95%. So 95%. And, so we put a multiply, we'll test positive. So and we'll test positive this direction. This is the probability we're searching, see? And when I put a circle here, or a square, let's say, it's the probability of going down this purple path, okay? Going down this purple path does not have a probability of 2%. That is another common mistake. The probability of going down that path is multiplying the A times the C, okay, which is in this case 95% times 2%. Now you might be thinking, how the hell do you multiply percentages? Most calculators can just kind of do that, but I'll take a moment to teach you some free math. So 95%, if you put it as a decimal, is 0.95. 2, if you put it as a decimal, is 0.02. What's an easy way to remember this? 1 equals 100% in realm of probabilities. So 50% must equal, you guessed it, 0.5. Okay, and if you remember that, you can kind of like reach everything else. See? Not that it showed up here, but if you were to have, say, 0.5%, then in decimals, that would be 0.005. Okay? So notice there what's going on. There's a couple ways to remember this. I prefer to just have this in mind. See? But hey, to each their own. Point is, if you feel weird about multiplying percentages, you can turn them into decimals. Dude, you should even turn it into fractions, my guy. Anyways, you go here, you multiply these two bad guys, and you end up with 0.019. If you don't like how this looks, then you can change it to percent by multiplying it by 100. You end up with 1.9%. Okay, so that is the probability that you will not have the disease and you tested positive. For the second part, we have that you will test negative. And so if you will test negative, there are two options. See? Let me erase what's going on here for a second. Make a little bit more space. So we're looking at will test negative. So in which scenarios, this is how you approach, in which scenarios do you test negative? I test negative here, and I test negative here. Well, all right, tell me more. How do you reach the first one? You reach the first one by first going through disease. So I am doing this times this. 5% times B%. See? And for the second one, we are going through test negative and no disease. So we're going through A% times D%. See? And I add both. I'm going to go over in a second why you're adding both. So remember when I said that and is multiply and or is add? Well, if you will test negative, then there are two options, right? Either you, actually I'm going to do it up here. If you test negative, there are two options. You either have disease and test negative, or no disease and test negative. So those are the two options for when you test negative, right? You have the disease and you test negative, or you have no disease and you test negative. So, just to make it more visual, disease. There it is. And there's a multiply. Test negative. The B right there. Or we put the add. No disease is A. And there's the multiply. Test negative, the D. So that is why we're adding, and that's why we're multiplying these scenarios. You have to think in terms of and or ors. So scenarios where you test negative are those. Okay, so I'm going to plug in what I have in yellow over here. It's going to look something like this. We have 5% we said was 0.05 times testing negative B, which we said was 1%, so 0.01. All of this being added, ¿cierto? To the alternative, which is A times D, ¿cierto? We said A was 95%, and we said that D was 98%. So all of this into your trusty rusty calculator, and you're going to end up with 0.9315. All right? If you don't like how that looks, you turn it into a percent. That is 93.15%. So this is probability of testing negative. That is for the second part. See? All right, awesome. Oh, just to write it down, here we said it was 1.9%. And we'll test negative, we just said is 93.15. 15%. All right, and now for the third part, we have has the disease given that they tested negative. So now that we're in the given land, we are into the weird shit section of the world of probabilities. And so given has a particular approach, okay? And it's so flippin' weird that it's in the formula booklet. And you know it's weird if it's in the formula booklet. And so your formula booklet has conditional probability, which is also for given. Okay, so when you see the word given, you have to think conditional probability. It is this guy here. Okay, and so the way you read this is probability of A given B equals that whole thing. Okay, so probability of A given B equals that. Okay, the formula. Point is, this line here is your given. Okay. All right. Anyways, so that is where I'm getting this formula from, just so that you know. And so if I go back to my tree diagram thing, we have has the disease given that they tested negative. And So we said it was P A given B equals P A and B, and on the bottom we have just P and B. And so the hard part here is defining what is A and what is B, and you work from there. Now, we said that it was A given B, and so A is before B in the word given. So anything to the left of given is going to be A, and anything to the right of given is going to be B. And so A and B is going to be has disease and tested negative. So has disease and tested negative, which is actually what we did for part A. So part A is exactly that. For part A, we found that we had to do 0.05 times 0.01. Okay, so that right now is plugging in for P, A, and B. All right. And at the bottom, which is probability of just B, we have that they tested negative. What are the scenarios where they tested negative? We have this scenario that goes like this, tested negative, and we have the scenario that goes like this. They also tested negative. Whoops, sorry about that. They also tested negative going through this path here, which is actually what we did for part B. And we saw that we had to do A times C. A times D plus 5% times B. See? So if I write it out real quick, we end up with, on the bottom, 0.05 times 0.01 plus 0.95 times 0.98. All right. So this is pretty consistent from what we did in this first part and the second part. They both sort of like combined onto the third one. All right, which is actually, side note, pretty useful for IB. IB in general is like, for the third part, you probably need something from the second one or the first. Okay, for part C, you probably need something from part A, from part B or part A. Okay, that is a very common trend and can be a big hint on how to approach what's coming. So that being said, that is how you plug into the formula. See, so probability of A and B is what we have on top. Probability of B is what we have on the bottom. This is literally what the formula is asking for. The hardest part is identifying what is A and what is B. Again, the buzzwords are huge. That's why I wrote the buzzwords over here. We have and, or, and given. Okay, those are our buzzwords. You gotta search for them, and that is your compass on how to approach these things. You plug everything into your calculator, and the probability of A given B, in other words, has the C's, given that they tested negative, is going to be just around 0.000536768. If you don't like that number, I want to turn it into decimal. That would be 0. Um, 0.0537%, let's say. Okay. So again, either of these works. That is the answer for this third part. Then they tell us that the medical center finds the actual number of positive results, because again, these are just probabilities, but the actual number of positive results in their sample is different than the predicted by the tree diagram, and we need to explain why this might be the case. Now, for these scenarios, there are a lot of different explanations that you can give. The most direct one, I think, is that the sample for convenience, as we said earlier, because it's the easiest path. The easiest path is usually not the best path, unfortunately. Okay, so you can immediately say that because the sampling method being used is convenience, then the sample is not representative. So you can actually say that. You can say here, sampling not representative, convenience, sampling sucks. You would use other words, but that's the main idea. Okay, you can also say sampling is not random, which is another way to say that it's not representative. Okay, and you can also simply say that, hey, the medical center is comparing observed versus expected, and it's very common for your observed values to be different to your expected. All right, the formula book, the answer key does have it like this. Okay, so just so that we're all on the same page, either one of these three is going to work. It's exactly what I just told you just now. But at the end of the day, the intuition is like, you got to hammer down on what's the sampling method, or also just say like in theory, the observed and expected is not necessarily going to be in line. Okay. All right. Awesome. So either one of those is going to grant you that 1 point. That is for part D. All right. And for this next part, they actually vomit like a lot of information. And they tell us that the staff at the medical center looked at the care received by all visiting patients on a randomly chosen day, and that all the patients received at least one of these services. They had medical tests M, seen by nurse N, and seen by doctor D. And then they give us like a lot of numbers. Okay, a lot of scenarios, a lot of numbers, and they give us the mission to draw party. See, draw a Venn diagram to illustrate this information, placing all relevant information on the diagram. So first things first, how many circles do we have? We have 3. How do I know? Because we have M, medical tests, N, nurse, and D, doctor. So now I'm going to go ahead and draw my Venn diagram. Make it nice and big. Give yourself a lot of space. I'm going to put a circle up here for D, doctor. Another circle over here for M, medical, where the hell, medical tests. And N for nurse down here. All right. And so first I'm going to commit a mistake filling in the Venn diagram. Okay, and I want you to really think about what is the mistake that I'm doing with my approach. Okay, so what a lot of people do right off the bat is that they see, okay, 78 have medical tests, so I'm going to put medical tests down here. We have 78. Then we have 45 were seen by a nurse, 45 over here, and 30 were seen by a doctor, 30 over here. So a lot of people, that's boom, the first thing they do. And that is unfortunately already a mistake. So take a moment and think why. For example, for 78 had medical tests, it doesn't say 78 had medical tests only, which can be a scenario, ¿cierto? But it doesn't say only. It says that 78 had medical tests. And so that 78, where is it in my diagram? That 78 is actually all of this. 78 is inside all of that, and this 78 that I wrote in, I'm going to highlight in red here, the way I put it in, which was the mistake, is that I thought it was only there. See, but that 78 is actually encapsulated in all of the yellow, not in all of the red. So that is a very common mistake people do when approaching these problems. If it said only, I would be correct in putting it in red. But since it doesn't say only, you actually have to kind of go like discarding from that 78 and see how much were actually only medical tests. So let's take that approach again. I'm going to erase my 78. I'm going to erase my 45, erase my 30, erase that highlighted thing, draw this again. And now that we have that knowledge, we will approach differently. See? And so yes, 78 have medical tests, but for now we're going to put these 3 on hold. Okay, it's useful information, but we do not plug it in right away. We had that 9 had medical tests and were seen by a doctor and the nurse. And so there's a lot of ands there. So 9 had medical tests and seen by doctor and the nurse. This is one thing that I can plug in directly. So this 9 can actually go here. And that actually already tells me that the 78 I had before needs to get subtracted by 9. The 30 that I have for doctor needs to be subtracted by 9. And the 45 that I have for nurse has to be subtracted by 9. And so you go subtracting until you reach the appropriate amount anywhere. 18 had medical tests and were seen by a doctor, but were not seen by a nurse. So 18 had medical tests, so that would be M here, and were seen by a doctor, but not by a nurse. So medical test, doctor, not nurse, it's going to be this guy here. So that guy there, we just said was 18. Bada bim, bada boom. 11, oh, sorry, and now that we said 18, over there, I actually have to subtract 18 from here and from here. Why? Because that 30 and that 78 is either only doctor or only medical check. Aha, now it's starting to make more sense. For this 11, we have that 11 patients were seen by a nurse and had medical tests, but were not seen by a doctor. So not seen by doctor, but had medical and nurse, it's going to be this guy here. We said that it was 11, so we put 11 here. And again, we subtract 11 from both. Why do we subtract 11 from both? Because that 45 and that 78 is only nurse and only medical check, respectively. We move on. 2 patients were seen by a doctor without being seen by a nurse and without having medical tests. So 2 patients were seen by a doctor without being seen by a nurse and without having medical tests. So that means that this guy here for doctor has to be 2. Ah, so 30 minus 9 minus 18, does that equal 2? Let's find out. So 30 minus 9 minus 18 is the same as writing 30 minus 27 equals 3. So if I'm missing 1, to reach that 2, I can also just say that it's 30 minus 9 minus 18 minus something has to give me 2. What is that something? It is this guy here. That guy there has to be equal to 1. Don't believe me? From here, we have 30 minus 27 minus x needs to equal 2. So 3 minus x equals 2. Whoops, equals 2. We have plus x to both sides, so we have 2 plus x. We have minus 2 minus 2, x equals 1. So this x here has to equal to 1. This guy here has to equal to 1. And so that, this whole thing here has to equal 2. And so that is the approach that you do to these kind of things. For this 78, if I do 78 minus 9 minus 18 minus 11, I end up with 78 minus, I can't math right now, minus 38. That gives me 40. All right, so this guy up here is going to be 40. And 45 minus 9 minus 11. It's going to be the same as 45. Oh, and also minus 1. I missed this minus 1 here because of this guy. My bad. So we have 45 minus 9 minus 11 minus 1. It's going to be 45 minus 21 is going to give 24. So this whole guy right here is 24. And that, ladies and gentlemen, is the Venn diagram that we're going for. And so again, the biggest mistake most people do is assuming that 78 have medical tests is medical tests only. You cannot assume that unless it says it. Okay, if it doesn't say it, you need to go subtracting from that 78, given the other information that they give us, and you kind of work from there. Okay, that's also why the IB trickily puts this first to try to make you fall into that trap. So careful, be very careful. That is for part E. We drew the Venn diagram, there it is. Part F is find the total number of patients who visited the center during this day. All you have to do there is add all of these guys up. So we have 2 plus 1 plus 18 plus 9 plus 40 plus 11 plus 24. You put all of that into your calculator. You end up with 105. So all of my guys added up together give me 105. That is for part F and for part 1. Alright, for this second one, we have that a farmer owns a field in the shape of a triangle ABC, such that AB right here is 650, AC is 1005, and BC is 1225. All of these in meters. So careful with your units. These are all in meters. And so for part A, they ask us to find the size of ACB. Now, would they write it like this? Find the size of ACB, and they put a little bit of thing on top of the C. That makes reference to an angle, okay? And so that little symbol there is asking us, okay, you need to find this angle here, all right? So we are looking for the angle of C, basically, that is between A and B. Now, whenever you are working with triangles in particulars, you should be thinking in trigonometry, okay? Trigonometry. And there's a lot of different tools we can use here. Mainly in our formula booklet, we have the sine rule and the cosine rule. Okay, these are the two rules we have, and they're going to come into play shortly. So let's go ahead and pull up our formula booklet. So here it is. I'm going to do Control F, cosine rule, see what's going on. See? So in our same formula booklet, we have sine rule, cosine rule, and area of a triangle. Okay, and the main thing that people sort of like miss when they're studying this is understanding well the formula. Okay, if you understand your formula, you understand your tools. If you understand your tools, you have a full grasp of your formula booklet. And the day of the test, you walk in and you have a pen, a pencil, an eraser, your mind, and the formula booklet. Okay, so you gotta get familiar with it. Let's see how this works. All right. Any big letter, I'm actually gonna write this over here. So big letter equals, whoops, how the hell do you make it equals? Big letter equals angle. Little letter equals side, okay, or distance, whatever. See? So if I go ahead and draw, say, a triangle like this, and I choose that this is wait, sorry, hold up, that this is angle A, then that means I have side little a. If I say that this is angle B, then I have side little b. If I say that this is angle C, that means I have side little c on the other end. Right, so that is why there's big letters and little letters in this case. And you will notice that this sine always goes with an angle, okay? Sine with cosine, which makes sense, see? But basically, as long as you have this in mind, that big letters are angles and little letters are side, you should be able to navigate these formulas without an issue. Also, keep in mind that A, B, and C is all like arbitrary. Like you choose what's A, you choose what B, you choose what's C. So in this case, we have 3 sides and we're looking for 1 angle, okay? The sine rule, you will see, has sort of like 4 parts to it. See, what I mean by 4 parts? Usually you work it like this. You have 1 angle, sorry, you have 1 side, a second side, 1 angle, a second angle. So if you have 2 pairs, you're good to go. In this case, I don't have pairs anywhere, see? Because I do have this distance, but I do not have that angle. I do have this distance, but I do not have that angle. And I do have this distance, but I do not have that angle, so I have no pair. As long as you have at least 1 pair, and you sort of have like 3 out of 4, that means like this one, and this one, but not the last one, then you can solve it. But in this case, we have no pairs. So for sine rule, even though we're not going to use it, it's good to have in mind, it works in pairs. Okay, that's like the big thing, right? Cosine rule, like if the sine rule doesn't work, cosine rule has to work. So like if you don't have pairs, cosine rule is probably what you have to use. Cosine rule is a little more funky, but let's see what happens. See? So in this case, as we said, we have a bunch of sides, but no angles, and we're trying to find 1 angle. See? And so if you notice here, we have one of the sides, right, with C, another side with A, another side with B. So here it is asking for all the sides, A and B repeats itself, and only 1 angle. Ah, so I'm looking for just 1 angle. Also, there are 2 cosine rules or formulas or whatever. We have the one on the left, we have the one on the right. They are quite literally the same, okay? It just moves some terms around. It's the same formula. In this case, I'm going to use the one on the right, just because it has the angle alone on one side, and it's easier to navigate. So, I'm going to write out that formula over on this side, okay? We said it's cosine C equals A squared plus B squared minus C squared divided by 2AB. All right, so again, big letter is angle, little letter is distance. And so here, since I said that C and A and B is completely arbitrary, you have to define it yourself. Now in this case, it aligns perfectly, okay, but that doesn't always happen. What do I mean by this? My C, in this case, is exactly the angle I'm trying to find that's alone, okay? So that's very convenient for me. But my C, quote unquote, could have been this one, okay? And then I'd have to be consistent in my formula. Why does this matter? Well, because you will notice that the angle you're trying to find, its distance has to be negative. The other two, you can switch them around. I mean, the positive, these two are being multiplied, doesn't matter. But you do have to capitalize on which angle you're trying to find, and from there, it goes on smoothly. All right, so that was a lot of explanations of how this works. But you will see that once you are familiar with the tools you have, the rest goes by really, really fast. Okay, and the main things I had to explain were what are the big letters, what are the little letters, and to make sure you're consistent with your formula. See? So I'm going to do cosine C equals a squared, which is anything but little c. So I'm going to say that a squared is going to be this guy here. See? So 1,225 big A little a, ¿cierto? Plus b squared, big B little b, minus c squared, this guy here, of course, right? Divided by 2 times 1,225 times 1,005. All right, awesome. So what you do from here, actually, and I missed opening this up. Give me 1 second. So what you do from this step is that you have to get C alone. See? So I'm going to have cosine C on the left side still, and everything on the right side I'm going to be plugging in. Okay? So bear with me for a moment. Da, da, da. All right, so everything on the right side is that. It is 0.8480. And a lot of people here just say, ah, this is the answer. See? And so that would be a mistake because you still don't have your angle alone. Remember that your angle is C. It is not cosine C, it is just C. And so if you want to get C alone, you have to do cosine inverse. So you do cosine inverse to both sides. I end up with cosine inverse of this, and that is my answer. So cosine inverse of this, bada bing bada boom, my angle C, or for part A basically, is going to be 31.9980, same as calling it 32. Now I'm going to take a moment and explain why we did cosine inverse, because I know a lot of people are confused by that. So in this step, we had cosine C equals 0.848, right? And so since we want to get this guy alone, we need to do the inverse, see? So this is no different than, I don't know, say you have 2x equals 4, see? And so if you want to get x alone here, you need to see what is affecting x. So x is being affected by 2. In which way? By being multiplied. What is the inverse of a multiplication? The inverse of multiplication is dividing. So you divide to get x alone. Divide to both sides, of course. You end up with x equals 2. All right, this on the left side is no different. What is the inverse of cosine? It's cosine inverse. So once you do cosine inverse on this side, all it really does is get rid of the cos, and you stay with the angle inside. And that's how we got 32. All right, awesome. So that is a pretty thorough explanation, to be honest, of part A. But there it is. For part B, they go on and tell us that the local town is planning to build a highway that will intersect the borders of the field at points D and E, where DC is 210 and CED is 100. Most of these things are already in the diagram as it is shown below. See? Awesome, awesome. So now we need to find DE. And so here what I like to do, especially if there's a new triangle that gets involved, is to draw it out. And so DE, when it's placed like this, makes reference to a distance. See, it makes reference to the side. It's this thing that's super mega bolded. All right? And so that triangle there, I'm going to draw it out. We have C, D, and E. And basically, I have to analyze what information I have. So I have 210 over here. I have the angle 100. And there's one more thing I have, see? Which, by the way, has to do with part A. See, part B usually needs things from part A. From part A, I got that angle C was 32, so that means that this guy here is 32. That also means that this guy here is 180 minus 100 minus 32. Why? Because there's 180 degrees in a triangle, so I subtract the other two, and I end up with God, how much is this? I can't math right now. It's 48. See, so that angle is 48. All right, point is, again, same approach. You're trying to find DE. So I'm trying to find one of the sides. It's this guy here. The first thing you do is you open up the formula booklet and you go from top to bottom. See? And there's only two options, so it's not that complicated. You want to prioritize using sine rule. If that doesn't work, cosine rule is going to be your savior. See? How did sine rule work again? What was the most important thing? It works in pairs. So do I have pairs here? Yes. I have big E, which is this angle 100, paired with the little e. Oh, interesting. And I have big C paired with the side I'm trying to find. So sine rule looks like this. We have little letter on top, big letter on the bottom with sine, and then the same thing on the other side. See? So this is no different. And once you get familiar with the formula booklet, this is how you start seeing it. You have distance 1 on the top, angle 1 on the bottom, distance 2 on the top, and angle 2 on the bottom. And so once you start looking at it like that, boom, it comes to your mind immediately. See? So in this case, my distance 1, we said was 210. Its angle 1, we said was 100. So we have sine 100. The other side, the distance we're trying to find, which we're just going to call DE. ¿Cierto? And its corresponding angle from part A is 32. So sine 32. So I'm going to go ahead and call DEX just because it's more friendly to write it out. So I'm going to put X here. This right here is going to be X. And I need to get X alone. So from this step, I can go ahead and cross multiply. So I have X times sine 100 equals 210 times sine 32. I still need to get X alone. X is being affected by sine 100. It's being multiplied. So I divide by sine 100 on both sides. And I end up with X equals 210 times sine 32 divided by sine 100. Awesome. I'm going to take one moment here and just point out why we don't use sine inverse here. The reason you don't use sine inverse in here is because sine inverse is only if you want to get the thing that's inside. So earlier we used cosine inverse because we were looking for the angle that's inside. See? In this case, X is being affected by sine 100, but it's just being multiplied by sine 100. Sine 100 is an actual number. You can go like this, sine 100, boom, it's an actual number, all right? So I'm basically dividing by 0.98 on this step here, see? But yeah, I just wanted to point out when and why you use sine inverse. More importantly, why. If you understand why in anything, it enters your head a lot more, see? So anyway, X is that. I'm going to go ahead and put it into my calculator, just so that you guys trust me. We have 210 times sine 32 divided by sine 100. That is that. We have that for part B. DE is going to be 112.9937. We also notice that this is worth 3 points. And because it is worth 3 points, we are probably missing something. We are missing our units. This is in meters. Careful. You can also write it out into significant figures, all the good stuff. You end up with 113. All right. Later on, they tell us that the town wishes to build a car park here. They ask the farmer to exchange the part of the field represented by angle DCE, and in return, the farmer will get a triangle of area ADF. So this triangle up here, right? So he's gonna lose CDE and get the thing in purple. ¿Vale? Where F lies on the same line as D and E, as shown in the diagram above, blah blah blah. And to find the area of triangle DCE. Now, when you are trying to find the area of any sort of triangle, you have two tools. Okay, so area of triangle. Your first option, which is the classic, is you do base times height divided by 2. The complicated thing here is that it's not always evident how to get your height. For example, in angle CDE, your height is like that. So you would have to find that, which is kind of hard, right? Um, anyways, um, that's your first tool. It's the classic. You know, it's what we're used to. It's based in height divided by 2. It always works, blah, blah. But there is another one, which is like the trig version. All right. So as we said earlier, we have area of triangle. It's right there. It is that your area equals, right? Big A in this case is for area. All right. So that's a little bit confusing. Big A here in this case is for area. Uh, your area is going to be 1/2 AB sine C. And so I know that looks a little bit weird, but let's take a moment and draw a triangle. See? So we have whatever. I'm just gonna call this big A, big B, little b, big C, little c. So this is stuff we're used to. So if we highlight a little bit, do I have a highlighter? Oh, I do. So little a, little b, sides. ¿Cierto? So boom and boom. Big C. Where's big C? It is here. Notice that big C is in between the two sides. And so whatever you define to be A, whatever you define to be B, you need the angle that is in between them in order to make this work. So if I'm looking at the area of triangle DCE, you need to see, okay, I could have this angle. Sorry, hold up. You need to say like, I have this side, and I need that angle. So that's one option, right? You can also say, I have this side and this side with D, and I have that angle. And then you can use the formula. And your last option is, I have this side, and I have that angle. Okay? So out of those 3 options, you might have noticed already which one is the most convenient one. Again, part C needs something from part B needs something from part A, etc. In this case, I have this side here, 210. I have this side here from part B, and I have this angle here, which I got it by doing the 180 minus blah blah from earlier. See, this 48 right there. So I'm just going to use that. So my little a is going to be 210. My little b, again, it's arbitrary, is going to be the x value from earlier, which we said was 113. So 113. And my sine C, right, the big C I should mention, so this C here is going to be 48. All right? So again, it's arbitrary. You choose how you define it. But once you get familiar with this tool, you notice that A, you need 2 sides and the angle in between, period. All right, there's a couple ways to remember it. That's the way I like to remember it. I'm a very visual guy, so I hope the highlighting thing helped. But yeah, that's all. Awesome. So I'm going to go ahead and use that formula. See? So we're going to have 1/2 times A, times little a we said was 210. A little b we said was 113. Big C we said was 48. So the area of my triangle is going to be this. This always works. You just have to be consistent with what you're plugging in. See? And the way you plug it in and everything. So I'm going to go to my calculator. We have 1/2 times 210 times 113 times sine 48. Okay, that's a pretty big number. We end up with 8,817.18, which is pretty much the same as putting 8,820 meters. Now meters what? Meters squared. Why is it squared? Because we're talking about an area. Meters to the power of 1, which is usually something you don't even write, is going to be a distance. Meters squared is going to make reference to an area. Meters cubed is going to make reference to a volume. All right? Awesome. So that is why you put those little numbers up there in the first place. That is for part C. All right, and last but not least, we have probably one of the most creative questions for this paper. We have that we need to estimate DF, and that I may assume that the highway has a width of 0. All right, what the hell is going on? DF is the guy that's up here. I'm gonna erase some of this because there's a lot of shit going on. So we need to find this distance here that it just drew in red. More than find, we need to estimate it. See? And so there's a couple assumptions we have to make in order to make this work. So essentially, if we're looking at DF, we're looking at that triangle there. See, so I'm gonna go ahead and draw it out. I'm gonna try to make it a little more artsy. So we have D, we have F, we have A. So we need to ask ourselves, what the hell do we know about this triangle? Okay? So what we know is that originally CA was 1005, and here there's 210. So that means that DA, ¿cierto?, is going to be 1005 minus 210. Okay? And that is, I feel like it's really easy, but I just can't think right now. So I'm going to use my calculator. 795. Okay? So that's the first thing. That side right there is 795. I'm going to draw it up there because I am tedious for my stuff. So that is 795. Okay? What else do we know? We know this angle. Okay? This is like a parallel lines property. Uh, this angle is equal to this angle, much like this angle is equal to that angle. Okay? And so way earlier we found that that was 48. So here we have 48. All right, and we need to find x or df. See? So we need to find x or estimate it. All right, so honestly, there's not too much you can do here, and you have to get very creative with it. All right? The biggest thing here, and this is an exercise that I don't like too much because it's a very specific hint. But there's one line here in this whole paragraph. That is one kind of cool thing about the IB. Like the stuff they mention in these paragraphs, like it's usually all used. It's not common that they put something that doesn't help you. Okay. So notice that for this deal where they make a car park, and they take some of this guy's farm, in return, the farmer will get a triangle of equal area ADF. So that right there is humongous. Equal area ADF. So this area here, whoops, didn't let me draw it. Hold up. Basically, this area that I'm going to draw in, say, brown right now, is the same area that is in brown over here. So, if we're talking about areas, that can be useful. We said that areas has two versions. See, we have base same side divided by 2 and the trigonometry one. Right? In this case, we're going to prioritize the trigonometry one. And so if I use this equation like right off the bat and just kind of see what happens, right? We know that the area was 8,820. See? 1/2, and here I need to put two sides. See? So, if one of the sides we're looking for is here, this x, ¿cierto? I'm going to go ahead and put x. The one that's adjacent to it is the 795. And the angle in between is the 48 right here. See? Sine 48. So again, that is very hard to notice, okay? And so the biggest hint I can give you is like, dude, anything the IB gives you in these paragraphs is probably going to get used. So highlight the buzzwords. In this case, I should have highlighted earlier, to be honest. Equal area. All right? That comes in clutch. And also, the other hint you can use, which is actually a prime example in this exercise, is that part B needs something from part A, part C needs something from part B, and part D needs something from part C. And so if you found the area of a triangle, you probably have to use that for part D. It's not always the case, but in this scenario, it came in clutch. Okay? So I have this set up, and now I need to get x alone. See? So it's going to look a little bit messy, but technically x is going to be equal to 8820 times 2. So that's this guy here being multiplied, divided by 795. That's this guy being divided again by sine 48. So that's this guy being divided. So all of that done makes me get x alone, as you see on the left side. So x is going to be equal to this. All right? So we take out our calculator. Bada bim, bada boom. We pull up that thing. Whoops. we put 8820 times 2 divided by 795 times sine 48. Ta-da! You end up with 29. Okay. Point, whoops, 8578, which is roughly the same as 29.8. So that is for part D. Some of you, if you're doing it along with me on the side, might have gotten a different number for this guy here. See? Or you might even notice that the formula booklet has it, the answer key has it different. The answer key has it on 29.8473, and we have 29.85. So there's a slight difference there. That difference arises because we used the estimated value from part C. We used 8820 instead of 8817. All right, and so that small difference is the kind of thing that makes you, you know, have a slightly different answer or whatever. But as long as you're consistent, you get full credit. Do not worry about that. I did want to mention it because I'm sure someone out there is facing that issue. Anyways, that is number 2. All right, so for this first one, we have that a new concert hall was built with 14 seats in the first row, and each subsequent row of the hall has 2 more seats than the previous row. The hall has a total of 20 rows. For part A, part 1, we need to find the number of seats in the last row. And so first things first, we need to identify what the hell is going on here. A couple buzzwords that can help us figure that out is, well, first of all, we have first row. We also have total amount of rows, and we also have subsequent row, or something about the previous row being added, right? 2 more seats can also be sort of a buzzword. And so the real buzzwords here, actually, if I'm more specific, is the 2 more, and the subsequent rows are big hints. See? So by now we should already be thinking that this is some sort of sequence, right? So we have a first row, then we have a last row, we have rows in between, we have stuff being added or multiplied. We're not sure. We're going to figure all that stuff out now. See? So we have two types, I should say, of sequences. We have the arithmetic sequences. I'm actually going to write this down, arithmetic sequence. And we also have the geometric sequence. And so as a quick rule of thumb or whatever, the arithmetic sequence is going to be adding or subtracting, while the geometric sequence, you guessed it, is going to be multiplying or dividing. All right, so in this case, are we adding or subtracting? Are we multiplying or dividing? Because we're adding 2 more seats than the previous row each time, we are indeed adding. That makes it an arithmetic sequence. So boom, that's the first thing you identify. This is an arithmetic sequence. And so in an arithmetic sequence, if we need to find the number of seats in the last row, what the hell can we do? There's a couple ways you can actually do this manually, but the most useful method, I think, is actually pulling up your formula booklet and looking at your options. And so your formula booklet, if you see here and you search sequences, you have 4. You have up top, you have the arithmetic ones. On the bottom, you have geometric. For this exercise, we will only care about the ones up top. And we have two formulas. We have the nth term, which is, say, like, if you're trying to find, I don't know, the 9th term, that would be your nth term. So n would be 9 in that case. And we also have the sum of n terms. See? And so since we're trying to find the last term, well, your n can't be last, because that's a word, not a number. But what is my last row? Well, oops, sorry about that. My last row is the 20th one. The hall has a total of 20 rows, so my last row is going to be when my n equals 20. Ah, now we're getting somewhere. So let me take a second and write down this formula real quick over here, just so that we're all on the same page. The formula was un equals u1 plus n minus 1 times d. So first of all, n is 20. See? So that is already a good starting point. Let's understand what is u1, n, d, etc. So n is going to be your nth term. See, so in this case, where is it that n is 20? D is going to be your common difference. Okay, that's also why it has a d on it. Common difference. And although this exercise does not have a geometric sequence, the R in geometric is like the same as the D in arithmetic. All right. So this is D for common difference, as I just said, and this is for common ratio. Okay. So that's why it's R down there. It's ratio. Ratio is for multiply or divide, and difference is going to be for add or subtract. See? So that's why it's a D in the first place. Might as well point it out. No reason not to. U1 is literally going to be your first term, and UN is going to be your uth term, if you want to call it. Okay. So depending on what n is, that's going to be your term, right? So the number of seats in the last row is going to be my U20, right? Why is it U20? Because there are a total of 20 rows, and my U20 is going to be the number of seats of the last row. So U20 equals U1, which you said was 14, right? So this 14 is U1, plus n, which we identified was 20, minus 1, times d, common difference. We're adding 2 each time. D is going to be equal to 2. All right. So you have this. You plug that into your calculator. You trust the process. You end up with all of this equaling 52. So U20 equals 52, which is the same as part A, part 1. Part A, part 2 is asking for the total number of seats in the concert hall. And so here we actually have to use the second formula. Pretty straightforward. In the first one, we were trying to find the nth term, in this case the last one, the n number 20. In this case, we're trying to find the sum of all the seats. See? Remember that in this scenario, U20 is the number of seats in the last row. Okay? And so if you add U1 plus U2 plus U3 up until U20, you're going to get the sum of all the rows. I mean, the sum of all the seats. See? Now, conveniently, we actually have a formula for that, which is down here. Now, let's take a close look at this, because a very common misconception is not knowing which one to use. If you see there's a semicolon here, ¿vale? That's telling you that either of these formulas works. Okay, they are both, legal. And so why are there two? Well, because they ask for different things. In what sense do they ask for different things? You need different things to make them work. For the one on the left, for example, that I'm going to do in red, it is asking for n, it is asking for u1, it is asking for d. So if you have those three things, you can use it. The one on the right also asks for n, also asks for u1, but does not ask for d. It instead asks for un. Okay? And so in this case, we can actually use both, I'm pretty sure. But I'm going to go ahead and use the one on the right because I want to. Okay? But, in some scenarios, you do have to use one over the other one. And your decisive factor, as you can probably already tell, is whether you have d or un. All right, that's the only difference between the two equations. The only thing that allows you to use one over the other. You can make the same analysis for a sum of geometric sequence, but actually, in this case, it's just some terms being moved around. They both need u1, they both need r, they both need n. All right, and so for geometric, the same analysis doesn't really matter. But yeah, I don't know. Just wanted to point it out. Anyways, so using the one on the right, I'm gonna write down the equation real quick so that we're all on the same page, which is Sn equals n divided by 2, parentheses u1 plus un. So I'm gonna plug everything in. See? And we already said it was 20, so S of 20, sum of the first 20 terms, which is all the terms in this case, S of 20 equals 20 divided by 2. Parentheses u1 we said was 14, this 14 here, plus un from part A, ¿cierto? Part A, part 1, which is 52, 52. All right, awesome. So if you plug all of that into your, whatever, calculator, you're going to end up with S20 being equal to 660. And that would be part A. All right, and now we have that for part B. The concert hall opened in 2019, and that the average number of visitors per concert during that year was 584, key number. In 2020, the average number of visitors per concert increased by 1.2%. For part B, we need to find the average number of visitors per concert in 2020. So, part B. There's a couple of ways to approach this. I'm gonna show my favorite one and explain the other method for for anyone else. But point is, in 2019, okay, we had 584 visitors. 2020, we had a 1.2% increase from last year. So we understand that, right? Intuitively, it makes sense. This year, in 2020, we had 1.2% more people than last year, and so essentially, we need to find how much that how much that increase is. And so my favorite way to do it is that you say, okay, I'm going to take my 2019 amount and add to it the increase. How much is the increase? Well, my 2019 times 1.2%. And so the next step is plugging in. See? So 2019 we had 584. So this is my OG, my original. See? And here is my increase. All right? This whole thing in parentheses is going to be my increase. So my OG is 584, that's from 2019, plus 2019 again, 584, ¿cierto? Times 1.2%. Now, how much is 1.2% in decimals? To be able to plug into my calculator. It's actually 0.012. Now, for anyone that is like, huh, what the fuck? Give me a second, see? A good way to remember how a percent turns into a decimal is remembering one or two key numbers. 50% is going to be the same as 0.5 or 0.50. I'd rather put the 50, but point is 50% is 0.50, okay? 100% is going to be double of that. It's just 1.00 if you'd like. 5% is going to be 0.05. And if you remember these three, or some sort of variation of it, I mean, you're good to go, okay? And so this 1.2, we're going to notice is going to be at the, for example, 1%, you can already tell it's going to be at 0.01. And if you want to do 0.2%, you're going to quickly identify it at 0.002. Well, you combine both, you end up with 0.012. See? Which is the same guy from here. All right, that's my intuition from percent to decimal, okay? So I plug everything, all of this into my calculator. I'm just going to show you what happens. I have 584 plus 584 times 0.012. And boom, we end up with that number there, 591.008. All right. If you want to do sig figs or whatever, that would be 591. All right. So that is for part B. The other way to do it, okay, that I like a little less, but hey, I'm going to show it anyway, is that you sort of skip. I mean, it's not that you skip, but this guy here, you put it in here immediately. All right. So this 584 in a certain way is like 100%. Okay. So what I could have done is that I do 584 times 100%, ¿cierto? Which is this guy here, 0.012. And this is also going to give you 591.008, practically 591. All right. And so the 100%, you can kind of like plug it in immediately, and you end up with this in pink or purple. Or you can do the thing where you do it separately. See? You do first the original one and then the increase. I prefer doing it like that. It makes more sense in my head. But hey, to each their own. Just to show you that it works. There it is. All right. But the intuition is that you put the 100% like earlier. See? I don't know. Whatever. To each their own. That is part B. All right, and later on for part C, they tell us that the concert organizers, right, use this data to model future number of visitors, and it is assumed that the average number of visitors per concert will continue to increase each year by 1.2%. And so here, a little similar to up here where we had 2 more seats than the previous row and stuff like that, here we have each year by 1.2%. So that is the big buzzword that should be telling you that this is more of a geometric sequence. See, so now for part C onwards, we're talking about geometric sequence. Are we multiplying or dividing? We are technically multiplying here because it is increasing by 1.2% each time. See, we're not adding by a flat amount. A flat amount would be adding or subtracting. Here it's not a flat amount. It depends on the last year. See, so we are talking indeed about a geometric sequence. So once we identify that, we pull up our formula booklet and ask it, yo, how can you help me out? In this case, it is asking for uh, the first year in which this model predicts the average number of visitors per concert will exceed the total seating capacity of the concert hall. So it is not exactly like the sum of like all the amount of the first year, the amount of the second year, the amount of the third year. No, it's like when it exceeds. See? And so the first thing is, what is the total seating capacity of the concert hall? Well, that is part A, part 2, which we said was 660. All right, so that is my total seating capacity of the concert hall. When does it get there? Well, that is when we use this guy. See? The nth term of the geometric sequence, that is going to be your current approach. So I'm going to write down that formula on the side, just so that we're all on the same page. Un equals U1 R n minus 1. All right? And so, U1, right, which is the average number of visitors, is 584. See? So we're going to go with UN equals 584 times R. What is R in this case? R in this case is simply going to be 1.2. All right? Now, R, because it is increasing by 1.2%, we actually have to write it as 1.012. A very common mistake that people do here is that they write it as 584 equals 0.012. All right? Why is that a mistake? Because if you take 584 and multiply it by 0.012, you end up with a dang small number. And so what that is actually doing is that it is decreasing 584 by, it is decreasing it by 98.98%. So if you want to increase it by 0.012, you actually have to do 100 plus that 1.2. That is going to be your percent. See? So 101.2% is this number here. All right? Common mistake. Be careful about that. All right? So we use the one on the top for the reason that I just explained, and we need to figure out what n is. All right? Now that is exactly the problem. See? Right now I still have two variables. I have un and n. Since we're talking about the total seating capacity of the concert hall, I'm going to choose for my un, whoops, sorry about that. I'm going to choose for my un to be the total seating capacity of the concert hall, which we said was 660. So 660 equals 584 times 1.012 n minus 1. All right, awesome. So now we need to figure out what n is and work from there. There's a couple ways to solve this, and my favorite one is the calc intersect trick. I do have a video that goes in depth with this, but basically we're going to go into our y equals, which is here, ¿cierto? And my y1 is going to be what's on the left, my y2 is going to be what's on the right. So what I'm basically doing is that I'm plotting these two lines and seeing where they intersect. And wherever they do intersect is what makes this whole thing true. And this whole thing is talking about an equals. And so wherever they do intersect is my value of n that makes it true, which is exactly the year in which the total seating capacity of concert hall is going to get exceeded or filled. See? So that is sort of like the intuition. Again, I do have a video on that, which goes much more in depth, but I'm going to go ahead and graph. See? Now, usually when you graph, you're not going to end up with the two lines actually showing up because well, that's life. See? So you do want to go to zoom, and sometimes zoom fit, which is zoom 0. Okay, zoom fit sometimes will make them appear. So that is usually my first go-to. I see one line up there, And the other line, does it reach? All right, it almost reaches. See, so they're almost intersecting. All I have to do is give it a little more x value. So I'm going to put x equals, dude, I don't know, I'll make it 15. See? And just to make it more pretty as well, I'm going to make my y equal to, say, 700. Right? So now I graph it, and now they should be intersecting. All right, clearly they are intersecting. So I'm going to go to second trace, hitting calc, go to intersect, pick my first curve. Yep, it's that one there. Pick my second curve, it's this one here. And then we have guess. Now guess is really only useful if you have more than one intersection, because it helps you tell the calculator which intersect you want, right? But just to be safe, you put guess on top of the intersect that you want, you end up with this value there. See? So I'm going to go ahead and write that down real quick. We have an x, or we have a set of points, I should say, of 11, 0.2559, comma, 660. All right, so this set of points down here is what makes this whole thing true. All right. And so how do I interpret this? Well, my 660 is here, and my 11.2559 is here. And so that's how the calc intersect helps me find any sort of variable. The reason I use this trick, I should have mentioned it, is that my variable was on an exponent, and it's fucked when it's in an exponent. It's hard to solve. This is my favorite tool. I showed it to you just now. I hope it helps. See? So anyways, n has to be 11.2559 in order to make this work. And within the context of the problem, we are talking within the year 2019. See? So 2019 plus a little bit over 11, so 11.2, is going to give me just about 2030. See? So 2030 a little bit onwards is going to be the year where the seats get exceeded. So that is part C. And before you ask, this is enough to show your work. I did this in the IB exam. I literally wrote, this is y1, this is y2, calc, intersect, wrote this set of points, and concluded it that way. See, this is a legit way to solve it. I assure you I got full credit. So yeah, that is part C. Alright, and now for part D, they tell us that it is assumed that the concert hall will host 50 concerts each year. And for part D, we need to use the average number of visitors per concert per year to predict the total number of people expected to attend the concert hall from when it opens until the end of 2025. And so we have 50 concerts each year, and per year the amount of people that attend changes. See? By how much does it change? By 1.2%, as we said earlier. Let us remember for part C that we already identified that R is going to be 1.012. That will be useful in a second. Now, because we're talking about a total amount, anytime you see total, you should probably be thinking of sum. Okay? If we're talking about a total amount of things, we're probably adding stuff. We're probably talking about a sum. If we look at our formula booklet, as I mentioned earlier, we have two scenarios. We have arithmetic on top, geometric on the bottom. In this scenario, we only care about the ones at the bottom. We have two formulas here, the nth term and also for sum. See, since we're talking about sum, again, we only care about the bottom again. See? So looking at the bottom, as I said earlier, there are two formulas. They both ask for the same stuff, so it does not matter which one you use. Because I am picky, I will use the one on the left. I just prefer it because whatever, it's just the kind of guy I am. I'm going to be using that one, all right? So just so that we're all on the same page, the equation I am using is, or the formula I should say, Sn equals u1, parentheses r to the power of n, minus 1, parentheses close, denominator r minus 1, all right? So let's go filling this in slowly and see what happens, all right? We already have u1, so that is my quickest one yet. We will say that u1 is 584. R, we said, was 1.012. N is yet to be defined because I haven't done it yet. And on the bottom we have R again, 1.012 minus 1. All right. So the hard part of this problem is identifying what N is. And so what a lot of people do here is that, okay, so we are adding from 2019 to 2025. So they take 2025, they subtract it to 2019, and they end up with 6. And they plug in that n has to be equal to 6. This is a small mistake, right? Like it kind of makes sense, like the process, but there's one small mistake here. And I think visually it's a great way to explain it. And so if I take 2019 and I have 2025 over here, and I put all the years in between, it will suddenly become very evident what the issue is. 2023, 2024, 2025. And so if I assign a number to each year, right? So this is my first year, this is my second one, third, fourth, fifth, and sixth. You will notice that from 2019 to 2025, there are seven digits. See? And so what the guy on the top does is that essentially you're saying, okay, from 2019 to the beginning of 2025. All right. But here, it is asking for until the end. Until the end of 2025. And so if it's until the end of 2025, you have to take the approach that I have on the bottom, and you realize that it's 7 years in total. Up here would be just, I don't know, like January 2019 until January 2025, which is different from January 2019 to December 2025. All right, so that is a very common mistake here. So that being said, n has to be 7. All right, so n equals 7. And so if I go ahead and do that, this whole thing on the left, I'm going to plug in 7 for n everywhere. See, so there's a 7 here, there's a 7 there. If I put all of that into my calculator, I end up with the following. Let's find out. So with 584 times this whole fraction, oops, let me do that again. Sorry, 584 times this whole fraction, which we said will be 1.012 to the power of 7 minus 1, parentheses close, oops, parentheses close. Bottom we have 1.012 minus 1, parentheses close. Okay, we end up with that number there. See? So 4,238.14. And here I'm going to put it in a circle and not in a square because we're not done just yet. We're not done just yet because this number here is the average number of visitors. The people expected to attend, right, the concert hall, one concert each year. But since we're talking about 50 concerts each year, I gotta take this number, multiply it by 50, and that is gonna be not my sum anymore, but 50 concerts each year added together will be my final answer. See? So just because there's a small line here that says 50 concerts each year, I gotta multiply by 50 at the very end. All right, so if I go ahead and do that, it gives me that number. So we have this 0.3, which is the same as putting this. If you like significant figures, it is the same thing. All right, I feel like I might have not explained it the best way at the very end, so let me go there once again. Point is, this S7 here, right, which gave, this whole thing here, so this S7 here, which gave me that number there, is the amount of people that attended like one per year. So if I take the sum of 2019, 2020, 2021, 2022, 2023, 2024, 2025, it's going to give me that number there. Okay? And the reason I multiply by 50 is because there are 50 concerts each year. And that is part D. All right, and now for this fourth one, they tell us that it is known that the weights of male Persian cats are normally distributed, those are huge buzzwords, with mean blah and variance blah. Okay, and for part A, we need to sketch a diagram above showing the information. And so, when we're in the land of normal distributions, we have three main tools, okay, that I'm actually going to put down here. They're these. Okay, and so I actually have like a cheat sheet. Um, we have normal PDF, normal CDF, and inventory normal. Those are my three tools. Where can I find those tools? In your graphing calculator. In your graphing calculator, right on top of vars, you have this little thing that says distr, makes reference to distribution. So you press the blue guy, you press vars, you go to the distribution. The first three tools are right there: PDF, CDF, inventory normal. Same stuff I have down here, right? And so as they show up, we will be using them. But just know those are your tools. Okay. A lot of the IB and a lot of my videos you're gonna notice is not so much knowing like some fancy math thing. It's just knowing the fucking tools you have and when to fucking use them. All right. So part A, we have to draw this. Okay. Sketch a diagram. We know it's normally distributed. A normal distribution is also called many times a bell curve. Okay. So we will literally draw a bell curve that looks like this. All right. And I'm just gonna say right away, the guy in the middle is this, which is your mean. Okay. And 1 over. Okay. You have your mean plus 1 of this. And that is your mean plus 1 standard deviation. Okay? So 1 backwards would be your mean minus 1 standard deviation, and you keep going like that. Okay? Now I'm going to take a moment and just say like why the normal distribution is a big deal in the real life. And it's because this pattern of like how stuff gets distributed actually repeats in a lot of ways. For example, if you take the average weight of a baby at birth, of like 1,000 of them, at some point you're gonna end up with something that looks literally like this. Okay? Why is that relevant? Well, because this area and this area makes reference to a certain percent. This area and this area makes reference to another certain percent. What am I talking about? Talking about that. So if you see what's in green, the big chunks, which is just one standard deviation over, makes reference to 68% of your population. Two standard deviation over, which is where I hit the yellow stuff, is 95%. Where I hit the red, which is way, way out, it's going to be 99%. Right? So just know that the normal distribution actually has like purpose behind it. Okay? I mean, most of math does, but I'm just going to point out, some of this stuff applies in real life. So, if we're sketching the diagram, we do have to go 3 standard deviations out. Okay, that's just the kind of thing that you have to be aware of. And so, there it is. Okay. So this is sort of like my base for drawing it, for sketching it. And my next step is filling in these numbers. Okay. So what is my mean? Well, they told us that the mean is 6.1. So I'm going to go ahead and I'll do it in red. Okay. So this mean right here is going to be 6.1. The number on the right is one mean, right? Plus one standard deviation. What the hell is my standard deviation? Let's see. Here we have variance. Okay, so they tell us that my variance is 0.5 squared. And I know that looks kind of weird, but they actually do that in a convenient manner. Why? Because your standard deviation is your variance square rooted. All right. So standard deviation in this case is going to be 0.5 squared rooted, which is just going to be 0.5. All right. The root and the squared are going to be opposites. Right? They are inverse functions one to the other. It just kind of crosses out. You end up with 0.5. So I can immediately say that my standard deviation here is indeed 0.5, which is not something that shows up in this exercise, but it's also why the normal distribution, if I were to write it out in very, very fancy math words, would be like this: 6.1, comma, 0.5 squared. Because the normal distribution, you write it like the mean and the variance, which is standard deviation squared. Okay? So that it's actually kind of useful that they put it squared in this case. You can tell that the standard deviation, which is just this, is just going to be 0.5. All right, that was a lot of blah blah, but it's a little bit of the context of what is the normal distribution and all that good stuff. See, so if I'm going to finish sketching this, I have to do 6.1 plus 0.5, which is going to give me 6.6. See, just so that we're all on the same page, here I did 6.1 plus 0.5. Why 0.5? Because we are adding one standard deviation. One standard deviation is this guy without the squared. See? Nailed it. So if I go backwards, it's going to be 6.1 minus 0.5. You end up with 5.6. All right, so that is my approach to sketching it. First, you have to draw it like a bell curve, and second, you have to plug in the right numbers. See? So if I'm just going to go ahead and do that on the left, I do minus 0.5 again, I end up with 5.1, minus 0.5, I end up with 4.6. On the right side here, if I add 0.5, I'm going to end up with 7.1. I do it again, 7.6. All right, so that would be for sketching my whatever, man. This is part A. Okay, this is for sketching. You have to do it that way. You have to plug in the numbers. Okay, it's not just about drawing the figure. You have to plug in the numbers. So that is part A. All right, and now for part B, we have that we need to find the proportion of male Persian cats weighing between keyword 5.5 and 6.5. So between 5.5 would be this guy here, and this guy here is 6.5. All right, so as I said earlier, these are 3 tools. You can take a quick glance and like already tell me uh, which ones we have to use. But I think it's more important to understand the intuitive method and like the the approach that I like to share, or that I hope that you learn when you watch these videos. And so like the whole point is that, I don't know, whatever. You're taking this test, you're like a little stressed out, and you don't really know what the fuck is going on. But you know that this is about a normal distribution, and you know that your calculator has some tools. And so that is the main thing like that I like to teach. Dude, what are your tools? How do they work? And so when you're in the middle of the test, you can kind of figure out which tool to use. No one, or well, no one is a strong word, but most people don't memorize which tool to use in which scenario perfectly. All right, but I do think it's very important that you know which ones exist, how to reach them, and intuitively figure out which one you're supposed to use. And so you somehow remember, or you will remember that there's tools in your graphing calculator, and so you know that it's in distribution, right? So you go second vars hit distribution, and you know that it's these 3. Now, you don't recall which one to use because no one has godlike memory, and so you go one by one and see what it asks for, and from there kind of tell what it gives you. And so normal PDF, I see that it asks for an x value, it asks for a mean, it asks for a standard deviation respectively. And so in this scenario, you put just one x value. Here, I have 2 values between 5.5 and 6.5. And so because I have 2 x values, that's already not good enough. I know that PDF does not help in this scenario. See? Um, and well, let's take a second and read. PDF gives us the percent of the data result that falls exactly on one given score, which makes sense. If I plug in only say 6.8, right, I'm gonna find the percent of nailing 6.8. See, of getting a cat that weighs 6.8. Let's go ahead and see what happens, right? So I plug in x value 6.8. Mean we said was 6.1, I think. Yes. Standard deviation was 0.5. And so the intuition here is that there's around a 29% chance of getting a cat that weighs exactly, careful, exactly 6.8. See, so that is PDF. Now in this case, as we said, PDF does not help because we are talking about a range. See, we are talking about between keyword 5.5 and 6.5. And so we're trying to find the proportion or the percentage of cats that weighs between 5.5 and 6.5. So we keep going. See, I'm actually going to go with inventory normal now. Here, it asks you to give an area, and again, you give mean and standard deviation. And so inventory normal works a little bit backwards, right? You were giving an area, say that I know, I don't know, that this here is 7%, but I don't know what this value is or what this value is. Inventory normal can help you figure that out, okay? And usually, actually, now that I remember reading this quickly, it would be like, you know that from here up until somewhere is 20%. But you're not sure what that somewhere is. You don't know the weight of the cat that goes here. Inventory normal helps for that. Okay? So just that we're on the same page of what our tools do. That's PDF, that's inventory normal. CDF, the one that we actually have to use in this case, the most intuitive one to my liking, simply asks for a lower and an upper, mean and standard deviation. The reason that it comes like this, which is -1, E99, this is basically like a very big negative number. Okay, and when they put E, I think it's just 10, right? So it's like -1 times 10 to the power of 99. So it's a massively negative number. Okay, so all that it's really doing in this scenario right now is that your lower end is all the way over here. Okay, but our lower end, we want it to be right here, which is at 5.5. So we're going to take this guy, change it to 5.5. So now our lower is not over here. It is indeed where I drew it before. And our upper end is going to be over here, which is at 6.5. So lower, upper, mean from the problem, standard deviation from the problem, paste. Boom, 0.67307. So for part B, because we got this number here, if you want significant figures or whatever, you end up with 0.673, which is the same as 67.3%. And so the proportion of male Persian cats weighing between 5.5 and 6.5 is 67.3%. All right? Awesome. Nailed it. So that's part B. Later on, they tell us that a group of 80 male Persian cats are drawn from this population. And we need to determine the expected number of cats in this group that have a weight of less than 5.3. And so, because we're talking about expected number, that should already be ringing a bell. And because we're talking about less than 5.3, that should also be ringing a bell. And so, what we need to do now, let me make some space in our little diagram here. If we're talking about 5.3 and less than 5.3, see, that means that we need to find the proportion or the area or the percent from 0 to here. All right, so that means my lower end is going to be very negative and my upper end is going to be at 5.3. So that is the first step to find the proportion of cats that weigh less than 5.3. All right, so calculator. Whoops, sorry about that. Normal CDF. My lower has to be a very negative number, which I could do before, like -1 times E times 99 and all that shit. But just make a very, very big negative number is gonna work. See, so again, intuition is what matters. I'm just gonna put a very negative, big negative number, and my upper is gonna be 5.3. Mean didn't change, standard deviation didn't change. I get 0.05. See? So I'm gonna write that over here. We found that the percent, right, of cats that weigh less than 5.3 is around 0.5. Sorry, 0.05 4799. Let me just make this a little more clear. That is a 0. All right, so this is the percent of cats that weigh less than 5.3 kilograms. See? And so if we're talking about the expected number of cats, expected number of cats in this group, of which group? Of the group of 80 male Persian cats. See, so group of 80. So I take this percent, I'll multiply it by 80, and that is my expected number of cats that weigh less than 5.3 kilograms. See, so I go ahead and do this. Pop it into my trusty rusty calculator. Boom. 4.38. 4.3839. If you want to get fancy, this is the same as 4.38. So in this group of 80 cats, my expected number of cats that weigh less than 5.3 is around 4. See, more specifically, around 4.3. 4.38. So, I know these are a lot of numbers on the screen, but essentially you're taking the your proportion and your total. So you take the proportion multiplied by total, that's going to give you your expected value, expected number. See? Proportion in this case is a little bit like probability, all right? So your probability times your total is going to be your expected number for what they were asking for. See? So that is how you treat expected number. See? You first need a sort of percent, and then you multiply it by a certain amount. Alright, so now for part D, we have that it is found that 12 of the cats weigh more than X kilograms and to estimate the value of X. Now, which 12 cats? Well, the 12 cats from the group of 80. Ah, so we're still talking about expected number, I see. Exactly. So down here, let us remember that I did point out a sort of equation for expected number or amount or whatever, which is expected number equals your probability or proportion of your area, ¿cierto? Times your total. So expected number in this case is 12 because we're talking about the 12 cats equals your probability or proportion. See, I'm just gonna put prop. See, so prop for proportion times your total, which in this case is 80 because there are 80, the group of 80 cats. See, divide both sides by 80 to get proportion alone, which is essentially my variable. Your proportion in this case is going to equal 12 divided by 80. See, and so that's going to give you, let's find out, 12 divided by 80, 0.15. See, I'm from this step forward, I'm just going to say right away, depending on which calculator you have, you actually can skip some of the steps I'm about to do. But I'm just going to show how you do with the TI-84 because it's what I have at hand. All right. But point is, this 0.15 is telling you that your X value, see, moving from left to right, ¿cierto? At some point you fill in 15%. So let's say that you fill in 15% around here. All right. So this is from left to right 15%. That means that I have a value of X here. ¿Vale? Now it's not exactly the value of X that I'm looking for here, because this value of X is any of the cats that weigh more than X kilograms. And this 50% again goes from left to right. So from 0% to 50%. ¿Vale? So essentially what I need to find is the top 15%. What I just found is the lower 15%. Right? Interesting. So I actually have to find, say, from here to here. Right? And this value of X is the one we're actually looking for. Okay, not the one that I have on the left, the one on the right. And so, why is it useful that I know that this area on the black on the left side is 15%? Well, because if I do, say, 1 minus this 15%, which is the same as doing 1 minus 0.15, I end up with 0.85. So let's take a moment and think about it. This whole thing in, say, red is equal to 1, okay? This thing in black that I put earlier is equal to 15. And so if you take away what's in black to the red, ¿cierto? You end up with 85%, right? And because these diagrams are like, these normal distributions are perfectly symmetrical, right? This top 15%, I mean, this bottom 15%, the same amount of areas as top 15% here, see? And so what that actually allows me to conclude is that intuitively, this guy, to reach up until there, okay, which is just taking the red and subtracting the black, you end up with yellow, which is 0.85. So that right there is going to be 0.85 as an area, okay, which is the same 0.85 here. So you subtracted the 15% over on this end, all right? That's how you can look at it. There's the 15%. The one, as I said earlier, was the red, sorry, which would be like everything. And you end up with yellow, which is 85. All right, so color coded, it's a little bit messy, but I hope you got it the intuition. Point is, everything in yellow is 85, see? And that is the amount of area you need in order to reach the cats that weigh more than X kilograms. Now, what the hell is X more specifically? Well, that's when we use inventory normal. As you see, inventory normal is asking for an area, see? So I go to second vars dist, inventory normal is asking for an area. So if I plug in the area, I should be able to get the X value that from then forward is what I need. See? So if I go ahead and plug in 0.85, mean of 6.1, standard deviation of 0.5, it gives me the X value of 6.68, sorry, 6.618. So 6.618 which if you want to get fancy, you can do the significant figures and all that stuff. You end up with 6.62. All right. So this x value here, which I of course did not draw to scale, but 6.62 onward, okay, is going to be exactly what I was looking for. So now that I'm actually drawing it like to scale or how it should look like, this in yellow that I'm going to put now is 85%, all right? And everything to the right of that is anything that weighs more than X kilograms, see? All right, part D is probably the most confusing one. So I hope it was clear that like, let me just make a mini review, ¿cierto? You know that you're working with expected numbers because we're talking about 12 cats, and you have to wonder where those 12 cats come from. They come from the group of 80. So that's when you know you're in the realm of expected numbers. And once you find the probability or the area of that, you have to remember that inventory normal is asking for area, so you probably have to use that. So we use inventory normal, we get the x value that corresponds, 6.62. So that is for part D. All right, and now last but not least for part E, we have that 10 of the cats are chosen at random, and to find the probability that exactly one of them weighs over 6.25 kilograms. So here, we are choosing at random, and we're talking about a group of 10. All right, so we have a group of 10 that's going on. I'm going to find the probability that exactly one of them fits a certain condition. Now, this is now sort of a different sort of distribution because we're trying to see if one of the cases fits a certain condition. Right, like that's like the big hint, whether they fit a condition or not. We are now talking about a binomial distribution. And so a binomial distribution is usually like, I don't know, flip 10 coins, 4 of them are heads. Probability, and you work from there. See? And so in this case, it's no different, just that your quote-unquote heads or quote-unquote tails has to do more with how much the cat weighs. See? So in this case, instead of flipping 10 coins, we have get 10 cats, and we have exactly one weighs over 6.25 probability, and that is, this is part E. Okay, I just want to point out that it's a binomial distribution because it's very similar to like the original scenario, which is heads or tails. Just that instead of heads or tails, we are seeing the condition of does it weigh over 6.25 or not. All right, so that's a little bit hard to grasp, but I think that's probably the best way I can put it right now. Okay, so binomial distribution, what do we have? Well, let's open up our calculator, go to the distribution area once again, so it's second bars, and scroll, see what's up. So you scroll for a bit and you're gonna end up finding that you have binomial PDF and binomial CDF. So you open up binomial PDF, see what it asks for. So it asks for trials. I'm just gonna put binomial PDF, it asks for trials, X value I think it was, yep, sorry, first a P and then an X value, all right? P is gonna be the same as probability, all right? Just so that we're all on the same page. Let's see now what binomial CDF is asking for. We can see that it asks for literally the same thing. All right, so this is unfortunately one of those things that you might have to memorize, but I'm sure if you play around with it or put the same values, you can kind of like have intuition of what it's giving you. All right, and so I'm just gonna say right away, binomial PDF and CDF ask for the same stuff. Okay, the thing is that binomial PDF, right? PDF, your X value is actually gonna be telling you like probability of that exact amount. So in this case, we're going for exactly 1, so we will be using PDF. But just so that we're all, informed, in CDF, your X value is probability of that amount or less. All right, so it's very different. One of them is exact amount, the other one is that amount or less. See? So that is the difference between PDF and CDF. Of course, we will be using PDF in this scenario, but they do ask for the same things. All right? Awesome. So trials is going to be 10. My probability is something that I have not found yet, and my X value is going to be 1. And so which probability are we talking about? We're talking about the probability that one of these cats weighs over 6.25 kilograms. So how can I find that? Well, I'll go to distribution, normal CDF. My lower is going to be 6.25. My upper is going to be, I don't know, a very big number. See? So this is going to help me find out the probability that any cat weighs over 6.25 kilograms. I plug in the mean, plug in the standard deviation, much like the rest of the problem. We get this amount, see, 0.382. So this is going to be 0.382. 0.88. See what? Why not? Why not? So now using this information, I can go ahead and plug it into the other one. We said it was going to be binomal PDF because we were talking about exactly one of them. See, exactly one of them. This is a buzzword. If you see exactly, you should immediately think, okay, we're talking about PDF, binomal PDF. And yeah, that is a key buzzword actually that can help a lot. If you find exactly, you should be thinking PDF. So, trials was 10. Probability is this thing that we just found. And X value we said 1 because we're looking for exactly one cat of those 10 weighing that amount. We get this, see? Which actually makes sense because if the probability of, I mean, if 38% of all your cats weigh more than 6.25 and you pick 10 of them, getting only one of them that weighs that amount would be like unlikely, see? And in this case, we did get an unlikely number. We got 0.05. 0.17. All right? And that, as a percent, is pretty much just going to be, or actually first doing the significant figures, 0.0502, which is no different than 5.02%. So that's a pretty low number. It makes sense that it's pretty low. And so yeah, that is part E. 10 of the cats are chosen at random. They're probably the one of them, exactly one, weighs over 6.25, is this percent down there. See? The biggest buzzword that I noticed near the end is exactly. Okay, exactly is a very big hint for knowing that it's PDF. Remember the difference between PDF and CDF. Yeah, that is number 4. All right, and now for the 5th one, we have that a hollow chocolate box is manufactured in the form of a right prism. Ooh, buzzword, with a regular, big buzzword, hexagonal base. The height of the prism is h centimeters, and the top of the base and base of the prism have sides of length of x centimeters. So we have the h height here, and the x's are there. So here, here, and technically also here, 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 and here. Let's not forget the bottom. See, so all of those that I just put in blue are gonna be x. Okay, cool. So for part A, they tell us that given that sine 60 equals square root of 3 divided by 2, show that the area of the base of the box is equal to that. Alright, so whenever you have a show that, okay, really, you just have to find the area of the base. Okay, like, I know that they use the word show, but just find the area of the base. Okay, and once you find the area of the base, your work, right, your procedure is how you show it. Alright, and so really, you need to find the area of the base, and they give you a hint. And so the hint is sine 60 equals square root of 3 divided by 2. So, let's see what we can do. The buzzwords here, as I mentioned earlier, are regular hexagonal, right? And so a regular shape, any regular shape, is going to have all of its equal, a lot of equal sides. See, so everything that I just put in blue is kind of like what makes it a regular hexagonal base in the first place. Because this could be a hexagonal shape, but all of its sides could be, you know, not the same, right? So in this case, they are all the same. That's what makes it regular, and that is already a big hint. It's a big hint because that actually allows me to do the following. Notice what I'm going to do up top, okay? Because all the sides are the same, I can actually go like this. Boom, 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 bada bim, bada bam. So now all of these are x, quite literally. All of these homies are x. And not only are all of these homies, all of these sides x, we also have 6 because we have 1, 2, 3, 4, 5, 6 triangles, and they are all what we call equilateral. They all have the same side, which means that they all have the same angle. And how much is this angle? Well, if they're all the same angle, and I have 180 degrees inside a triangle, take 180 divided by 3, I get 60. So each of these sides is actually 60. All right, so that right there is massive progress. So now the the area of the base, right, which is this whole guy here, we just identified is actually just 6 triangles, and those 6 triangles are all equilateral. And so if I find the area of one of these triangles and multiply it by 6, I get the whole thing. See, so I find the area of one of them, multiply by 6, we're good to go. So what is the area of one of them? Well, how do you find the area of a triangle? You have two options. Area of a triangle in your formula book sheet has the classic, which is base times height divided by 2. And the other one, more new probably, is trigonometric. See, you have 1/2 equals, area equals 1/2 times a times b times sine c. So this is where I'm getting my formula, just so that we're on the same page. Is that it? So for your formula book, the area is going to be 1/2 times a times b times sine big C. Now, if you've seen some of my other videos, you know what little a and big A, little b, and little c, big C are, okay? But just as a very quick recap for anyone watching this, whatever, for the first time or anything, if I have this triangle, all right, the angle inside, for example, here, is going to be a big letter. So this could be angle A, which has side little a. This could be angle B, which has side little b. These can be angle C, which has side little c. So the big letters are angles, the little letters are sides. So if I apply, okay, this same formula from here, the area of one triangle, it's going to be 1/2 times x, which is a, times b, which is going to be another x, times sine c, the angle in between, is just going to be sine 60. And since I know that they told me earlier that sine 60 is this guy here, I suddenly have 1/2 times x squared, because x times x, times square root of 3 divided by 2. If you want to get fancy and combine terms or whatever, you actually end up with x squared times square root of 3 divided by 4, because we have 2 times 2 on the bottom. See? Awesome. And from this step forward, since this is the area of one triangle and I want to find the area of the whole base, I take this guy, multiply by 6, right? And so I have 6 times x squared, square root of 3 divided by 4. I simplify the 6 and the 4, so I divide both of them by 2. So this goes to 3, this goes to 2. I end up with 3 x squared square root of 3 divided by 2. So this would be the area of what I'm going to draw now in yellow. The area of all of that is going to be this, which is part A. Alright, and for part B, we have that given that the total external surface area of the box is 1,200 centimeters squared, show that the volume of the box may be expressed as blah. So we have surface area and volume. Those are the two things that we're working on. We probably have to use both. Alright. So let's go up here and let's do the surface area version and the volume version and see what happens. Alright. So surface area of this figure, there is usually not really like a formula for like the surface area of an entire sort of like object or shape or whatever. But you do have surface area for many other things in your formula booklet. So over here, for example, if I go to surface area or surface in general, we have curved surface area of a cone, of a sphere, of a cylinder, and also area in general, which can help for surface as well. Parallelogram, triangle, trapezoid, circle, etc. See, so very general stuff. Not quite what we're going for. And so for surface areas, many times you kind of have to eyeball it. See, so in this case, we have two regular hexagonal bases. See, so I have the one up top and I have the one down in the bottom. So I'm going to write that right now. Surface area equals 2 of the hexagon thingies. Plus all of these guys that are going down the middle, ¿cierto? Which are 6 rectangles. So this guy here, 1, 2, 3, 4, 5, 6. I also have those 6 rectangles. See? So I also have 6 rectangles. So I'm going to plug in on the left side what we have. So surface area, we were told actually from part B that it is 1,200. See? So here we have 1200 equals 2 times the hexagons. The hexagons are actually what we had in yellow this whole time. So we have 3x squared, square root of 3 divided by 2, plus 6 of these rectangles. And now the rectangle, what is the area of that? Well, whoops, we have height and the side down here, x. See? So we're going to put 6 xh, right? Straight from the diagram, there it is. Perfect. So now if I go ahead and sort of work around with this, I end up with 1200 equals 3x squared, square root of 3, because this 2 and this 2 goes away, plus 6xh. All right, so that is for surface area. And now for volume, okay, then we go ahead and work with volume for now. What the hell is the volume of this? Well, we go to our formula booklet, search volume, see what we find. So for volume, we have whatever that is, of a cuboid, of a cylinder, of a prism. See, and so for volume of a prism, we have big A and H, right? Where big A is the area of the cross section and H is the height. So H is the height, we have that, or I mean, not literally, but we know that it's H. And the cross section again makes reference to what's in yellow. Okay, it's basically the base of your prism. Right, the base of your prism is going to be the cross section. It's going to be big A, right? So this whole guy in yellow is going to be big A. So volume in this case is big A times H. Big A we know is what we said was in yellow. So 3x squared, square root of 3 divided by 2 times H. So right now I have two equations, right? I have the volume one, I have the surface area one. I have two equations and two variables, see x and h. So essentially, if I have h in terms of x, which would be the same as having h equals something something x, I can plug that in over here, and I end up with just x. So our main goal right now is that I go from two equations to just one, and having just one variable instead of two. So we're going to have h equals something, right? Why do we want h equals something? Because the formula for my volume over here has only x. It has only x, so that is what I want to reach. Only x, get rid of your h. So for this guy on the left, the surface area, I'm going to have h equals something, all right? So for getting h alone here, I first need to start off by subtracting 3x squared and square root of 3 to both sides. So that makes this go away over here. 1200 minus 3x squared, square root of 3 equals 6xh. I still need to get h alone. What is it being affected by? By a 6 and by an h, it's being multiplied. So I do the inverse, divide. So divide both sides by 6x. I go like that. See? So 1200 minus 3x squared, square root of 3 divided by 6x equals h. If I want to keep on simplifying, well, first of all, I'm going to put h on the other side because I'm picky. But also I can split this fraction in two, actually. And I end up with 1200 divided by 6x minus 3x squared, square root of 3, 6x. So I split it in two just because visually it's more appealing, but also for simplifying, I find that it's easier. And so on the left side, I'm going to end up with 1200 divided by 6, 200. So 200 divided by x. And for this other guy, I end up with just 1x on top, square root of 3 divided by 2. If anyone's confused what happens to the x's in that case, if I have x times x divided by x, I get rid of 1 on top, 1 on the bottom, I end up with just x. See? This is no different, this scenario that I just showed, to this. It's literally the same. In fact, this is the same as this, is the same as this. Because I get rid of this guy and this guy, you end up with 2x on top. See? Alright, that was like a mini session on exponents, and you know, we have x's like that. See? Alright, anyways, this is my h. Alright, so as I said, now that we have the height, we're gonna go ahead and plug it into the volume. So volume equals, well, the same thing I had before, 3x squared times square root of 3 divided by 2 times h. So all of what I'm plugging in now is h, this guy here, see? It's going to be 200 divided by x minus x square root of 3 divided by 2. All right, so that right there is h. See, all of this. So since we're multiplying these two terms, right, I can go ahead and distribute. So this times this, and this times this. For the first guy, I end up with 3 times 200, that's 600. So 600 x squared, square root of 3, divided by 2x. And for the other term, I end up with 3x cubed, because I have x squared times x, times square root of 3 times square root of 3, divided by 2 times 2, 4. All right, so let's take a moment and simplify some of these terms let's take a moment and simplify some of these terms. 600 divided by 2 is just going to be 300. The x squared on top of interacting with the x on the bottom, as I mentioned earlier, is just going to be x and square root of 3. So that is for the term on the left. And for the term on the right, I end up with 3 times x cubed times 3 because because these two guys combine. See, I end up with inside square root of 3 times square root of 3. I end up with square root of 9. Square root of 9 equals 3. Right? So those two guys actually combine. That is how square roots interact. So that is why I ended up with times 3 over here, divided by 4. See? And since I have times 3, as I'm putting in red, that actually just turns into 9 over here. All right. So that is it for the term on the left. This is for the term on the right. This is what I got for volume. I compared to what I had earlier, or to what I had to show, sorry. We have that volume equals 300 times 3 times x, times square root of 3 times x. This is practically the same, just this is flipped around, it doesn't really matter. Minus 9 divided by 4, x cubed. 9 divided by 4 times x cubed. Awesome. So that is how you show for part B. It's very important that you notice that you have volume and surface area going on. Of course, you need to combine them in some way. And the biggest hint for which that way should be is that originally I faced the problem that I have x and h as variables. Down here, as the final answer, there is no h, we have only x. So that is like my compass, that is my north. Make sure you end up with only x's, see? And so if you just try to do that, eventually you will find, or you will arrive to the answer. So that is for part B. Alright, then now for part C, we have that we need to sketch the graph of v equals blah, blah, blah. So my volume formula, or function, for x between 0 and 16. See? So whenever you're sketching a graph, it's very important to put key points. All right, so let's see how our graph looks like in the first place, and then we, well, highlight what we need to highlight. See? So I'm going to go to y equals, go ahead and graph it, and then sketch it onto my paper. Square root of 3 times x minus that fraction, which is 9 divided by 4. Right next to it, we have x to the power of 3. So I go ahead and open up my window immediately, and they already give me my domain, right? My values of x from 0 to 16. So I'm going to put minimum 0, maximum 16. And my y values, well, I can eyeball them later. But since we're talking about volume, I would assume it's kind of big. So I'm going to put minimum 0, maximum, I don't know, maybe 1,000. My scale for some reason is on 1,000. I'm going to change it to 10. To each their own. I go ahead and graph. All right, so clearly we can see that it goes up and then it goes down. So it probably looks something like this. It probably looks something that goes like that. Okay? So of course I can't sketch what I have right now. Like if I put this as my answer, it's terribly wrong. Okay? It's terribly wrong because you really, really, really want to show key points. The only key points you can show now is 0, 0, whenever it touches here, and nothing else. And showing the maximum value is always going to be important. See, so I want to make sure that I can show the maximum value. I'm going to keep playing around with my calculator for just a little bit more. I'm going to change my window again. Let's put 2000 just to make sure that we can see it. Graph. To my surprise, we still cannot see the maximum. But this third attempt might show to be promising. I'm going to go ahead and put 5000 because why not? All right. So I have a lot of that is additional. I'm going to change this just a little bit. Again, it's the IB. You just want to sketch it nicely if you can. All right, there it is. So my window right now is this is 0. This is 3,500. And this is 16. All right, so it's because you're sketching, you always want to highlight the key points. So as I said, the key points are going to be my maximum and where it touches here. Technically here it touches on 0, 0, so might as well write it down. Let's find out what my 0 is. So second calc, 0, left bound, right bound. So I'm going to do left bound over here, right bound all the way where I can't even see it, and I guess where my 0 is. Boom. So my 0 is going to be at 15.196, 0. And my maximum, more importantly, calc maximum, my left bound, I put it behind my maximum. My right bound over here. My guess somewhere near. There it is. So my maximum is going to be 8.77, if I remember correctly. 3, comma, 3,039. 0.34. Why not? All right, so that is good enough for sketching, honestly. Putting the scale also here is going to help. But for example, maybe putting the 8.773 here is not a bad idea. Got it? Maybe doing a dotted line, something like that can help. But what's going to net you the real points is going to be writing down the coordinates of key points, identify which ones they are as well. See? So in this case, it was the zeros and the maximums. Just like any parabola, really. Let's be honest. So that is for part C for sketching. Next, we need to find the expression for that. Now, what the hell is that? Well, that makes reference to a derivative. So my volume equation formula thing, following from part B, we have 300 square root of 3 times x minus 9 over 4 x to the power of 3. Now at this level, at the IBAISL level, we will always do the exponent derivative. Okay, how do I know it's a derivative? Because of what's written here. See, when you put dv over dx, it's telling you do the derivative of your function v. So it's going to be this whole guy here, and respects to x. So only to that variable there. See? All right. So before we do the actual exercise, I'm going to first show a quick example. All right. If I have x squared, f of x squared, and I ask you to do the derivative of this, see? So d of f of x divided by dx. What happens intuitively is that this 2 is going to go in front. The x is going to stay there. And the exponent gets subtracted by 1. So 2x, 2 minus 1 is 1. Same as just 2x. So again, the exponent goes down. You subtract the exponent by 1. And that's it. See? I know it's a little bit weird, but actually, derivative of an exponent is right here in your formula booklet. So if you ever forget it, you can check for it there. It looks a little weird because they put n in between and stuff like that, but it's no different. The exponent goes in the front, there's the n, and you subtract by 1. Bada bam, bada boom. So that is the derivative of x squared. See, that's what happens in this scenario. Let's see what happens when there's numbers in between. See, when there's numbers in between, by the most part, for now, you kind of don't give a shit. See, kind of. So in this case, we have the 300 with the square root of 3, which is next to the x. So this has to be multiplying, of course. The exponent up here is a 1. So I multiply by 1, and then I have x times x to the power of 0. All right, I know that looks weird, but I'm going to leave it there like that for now. On the right side, I have 9 over 4 times 3, because the exponent of 3, times x, 3 minus 1. See? All right. So that is like the first step. Now it's like seeing what happens to the numbers. See? On the left side, it's all going to stay the same, except for the x to the power of 0. which is actually just 1. So this is actually times 1 times 1. It's the same as if they just don't exist. All right. For anyone that's confused about that, I'll show you a quick example. See, if I have 2 to the power of 3, that's 2 times 2 times 2, which is 8. 2 to the power of 2 is 2 times 2, which is 4. 2 to the power of 1 is just 2, which is 2. And 2 to the power of 0 is going to be 1. Why is it going to be 1? There's a couple ways of looking at it, and the one that's most intuitive to me is that if I go up like this, I am multiplying by 2. So 2 times 2 is 4, 4 times 2 is 8. That is how you go forward. See? If you go backwards, you divide by 2. So 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. Ta-da! That's why it's 1. See? Awesome. The same applies for, I don't know, 3 squared. 3 squared is 9, 3 to the power of 1 is 3, 3 to the power of 0 is 1, because you divide by 3 to go down. Anyways, that's a quick way to remember, or the explanation better said, of why anything to the power of 0 is always just going to equal 1. So back to the exercise at hand, the term on the left ends up like that. The term on the right ends up like this. 9 times 3 is going to be 27 divided by 4 times x, 3 minus 1, 2. So that is my trusty, rusty derivative in this scenario. And now for part E, we need to find the value of x which maximizes the volume of the box. Now actually, with how we approach the problem, we already did that from part C. We did that from part C by using our calculator. So actually, part E is already solved. If you want to show your work, you would have to say, I graphed with these values and I did calc max. And you're good. Like that's literally it. Say you're good. That would be part E. If you want to solve it like sort of like the classical way, or how it's intended to, quote unquote, even though both work and both are in the answer key, because in part D we did the derivative, you can use the derivative to solve this. And so derivative, once you do the derivative of anything, you are now talking about slope, or rate of change. And so where your rate of change is equal to 0 is basically asking your function where, or when is my function, where does my function have a slope of 0? So having that concept in mind, here it's a slope of, I don't know, 3. Here it's a slope of, I don't know, 2. Here's a slope of 0. Anytime it's horizontal, it's a slope of 0. Look at that, how convenient, it's right at the maximum. So if you make your slope equal to 0, your first derivative equal to 0, you can find the value of x, which gives you which reaches the maximum, right? So if you solve this, finding a value for x, you will find that you end up with 8.773. See? If you're not sure how to solve this from this step because you have x squared on this side, there's a couple ways you can do it. See? I'm going to show you the classical one. So you want to get x squared alone, all right? So first things first, I don't like that there's a negative with the x, so I'm actually going to do plus 27 divided by 4, x squared to both sides. So I have this on the left side. On the right side, I have just this. I want to keep getting x alone, so I'm going to start by multiplying by 4 to both sides. So I end up with 27 x squared equals 300 times 4 times square root of 3. Divide both sides by 27 to keep getting x alone. I'm running out of space, but I think I can do it over here. So we have x squared equals 300 times 4 times square root of 3 divided by 27. And to finish getting x alone, I'm going to do x equals square root of that whole thing. Now I know that some of these values I could have simplified them before, for example 300 times 4, but what matters to me much more is the process. See, so I get x alone, I do the square root to both sides in order to get rid of the exponent, and we end up with something that looks a little nasty, but it'll give us the answer because we followed the method. If you follow the method, you will always get there. So 300 times 4 times square root of 3 divided by 27. Boom, 8.7738, which is the same 8.773 from up here. So I just want to show like the sort of classical way to solve it. But hey, both work. See? If you ever have to find the minimum, this is no different. Okay, at the minimum, if you look at the slopes, see? This has a slope of negative, I don't know, 3. This has a slope of negative 1. And this has a slope of 0. So that right there, at either max or min, you will always have that your derivative, in this case dv dx, has to equal 0. So yeah, rule of thumb, if you have the slope equal to 0, you're going to find the x value of your max or minimum. Awesome. So that is for part E. For part F, hence or otherwise, find the maximum possible volume of the box. Here it has to do more with like the context of the problem. And so the context of the problem for x is going to be, it has to do part of like a distance. See? X is part of a distance in this scenario. And your y value is going to be volume. See? Why is your y value equal to volume? Because this v on the left side is usually going to be y. See? What is your y in this case? It is this guy here. Let me use a more vibrant color. So this 3039 is the volume when x is 8.773. And when x is 8.773, we are talking about the maximum. So at the maximum, in other words, the maximum amount of volume is going to be 3039. So actually, for part V, we sort of already solved it. For part for part F, you're going to have that it's 39.34 centimeters cubed because volume. If you want to be consistent with significant figures or whatever, you can go like this. So that is for part F. Technically, we already did it before. But A, context matters. Interpreting your results matters as well. See, so whatever your x value is the maximum, that also makes reference to the maximum of your volume. See? Down here we have x values from 0 to 16. Up here from 0 to 3,500 we have our volumes. Bada bing, bada boom. There we go. Lastly, we have that the box will contain spherical chocolates, and the production manager assumes that they can calculate the exact number of chocolates in each box by dividing the volume of the box by the volume of a single chocolate and then rounding down to the nearest integer. All right, you might want to read that twice, all right? But point is, this is one of those sort of questions that you can answer like theoretically or with words, all right? And so what are a couple things that our manager is doing wrong? Well, the first of all is that here it says that the manager assumes, so this guy's assuming, so that is already like a small mistake, that they can calculate the exact number of chocolates. And so if you're doing an assumption and you think that's going to give you an exact value, you're a little bit wrong. See, it's going to be like a little bit off. See, so that is already one way to answer. And so yeah, I'm just going to write that for now. So one way that he's wrong is that the values aren't mega exact. There is wasted space. All right. And also, you can say that the model that we worked on, see, uses, and this is straight from the answer key actually, uses external values. So in other words, like volume has more to do with what's inside, while surface area, which is what it started from part B, has a lot to do with what happens outside. See, so we worked with area of the base outside, stuff like that. It's not as consistent. See, it would not be wise. You can look at the answer key, but anyways, I'll pull it up now just so you take a moment and read it. But really for part for part G, you can't just kind of like talk about it. See? So wasted space or spheres do not pack densely, which is basically like they don't pack like water. There's always going to be a little bit of gap of air between them. Or as I said, the model uses exterior values, stuff like that, etc. You don't know how thick the packet of the chocolate is either. Point is, this is worth 1 point, dude. And there's a lot of different things you can say. So you do not have to say all of these 4 things to get 1 point. As long as you say 1 out of 4, you're good to go. So that's also why at this point in time, I kind of just like spit ideas. And hey, whichever one you remember the most is probably going to be the most useful one. What I like to do for these exercises is really take a good read at what it's saying, and you will always find something that's like a little wrong. So first of all, as he said, the manager is assuming, and he thinks that he can get an exact number of chocolates. So exact is a strong assumption. There's got to be something a little bit off. Probably some space in between is what makes more sense to me. So that is why the manager is incorrect. There's lots of reasons. That's my favorite one. That is how you solve paper 2, specifically number 5. I hope it helped. Take it easy. Hey man, we'll see you around. Peace.